ते पीपीटी तो नहीं है बट आई थिंक हाँ स्क्रीन हाँ अंजलि वी कैन स्टार्ट नाउ बिकॉज 3 o'clock देयर इज अनदर लेक्चर.
So can I start?
हाँ yes yes now you can start.
Okay. Good afternoon, everyone. My name is Anjali Chakrayat, and I'm a research scholar under the supervision of Dr. Amit Mahesh Joshi and Professor Vinay Savla sir. Right now, I am my research focus on EEG-based brain computer systems. Sir, give it me a chance to show what I am doing right now. So, today's lecture, I am showing EEG pre-processing and how we work on imbalance data. So, first of all, we are going on data pre-processing. I hope all are my screen visible to all of you, and I start from here. Am I audible? Huh?
You are audible.
Okay. So first of all we know EEG data is basically a brain signal, and I hope you all are familiar from Google Colab, and you already learned like how we create a notebook on Google Colab and how we mount a drive to Colab. So first step is that we download data from a website. So here I take a MIT database, basically that database related to seizure, epilepsy seizure. So I download here two files. The name of file is CHB0103, and I manually also download that file. These are the two ways. Either you choose URL link, or you download manually dataset and then mount from your drive. So first, itself, here you will see that if mount a drive, you are able to see your dataset in your drive. Now, in second cell, we like we install few libraries, which is MNE library, SIPY, NumPy, Matplot library. MIT library basically we use for EEG signals or brain signals, work with that signal. NumPy library we use for handling arrays or mathematical stuff. If we talk about SIP library, so if we apply advanced signal processing, so that's why I add this library as well. And if you want to see your plots or your graphs, so we take it Matplot library. So first of all, I show all these cells and then I run whole the cell. But if you run this, so these a way that your library installed in your Google Colab. Then here you import MNA library, and I will show you. Maybe it will take time. So on my drive, place where this file here, this file. So the file we downloaded. So we read that these files. So basically, EEG files are recorded in .edf form. So our form is .edf. So I write a code, our raw data, mne dot io, it's input output, dot read raw edf file. So that means this command read your file, and the preload equals to true. That means it will load your whole data in this file. So in next command, I print all the information of the file. So you will see here that what are the information in our file. So if you already learned that EEG will take data two types, unipolar and bipolar. And this MIT database is bipolar data collection. So here you see that the channel name is FP1 to F7, F7 to T7. So kind of here is bipolar data set. Total number of channels 23 channels. Uh, Whenever we collect our data, uh, we set a frequency between high pass to low pass. So we set our high pass like zero point 0.0 hertz, 0.0 hertz. So below that frequency, we already removed, and above 128 hertz, we already removed. So we just take it our frequency from 0 to 128 hertz. And our sampling frequency is 256. So using this, if you want to see your data information or your signal information, you can see. Then before start this, I want to show you like how your EEG data look like. So here I just give it a command that your raw EEG data, and it plot your data file. You have a 23 channels, and within the duration of 10 seconds, it automatically scale your signals. I show you that this kind of signal you see like, so within a 10 second of duration, here all 23 channels of data here. Then I save the raw data in a particular file. Why I save it, I'll explain you later. Okay, so now up to you see that how we load our EEG data and how it look like. But in our EEG data have a lot of noise. Whenever we collect our brain signal through the EEG, a lot of type of noise added in our signal, just like eye blinking, muscle noise, power line noise, environmental noise, a lot of type of noise added in our signal. So we have to remove one by one these noise from our signal. So using band pass filter, we remove our slow drift noise, which is basically if a person move when we collect signal, or if sweat come to the person, that time also a kind of noise generated. So we remove that noise using low pass filter. Here you will see that we apply low pass filter. And Also, I remove high frequency noise. This is basically related to your muscle activity or your device noise. So, uh, before, when our signal collected EEG data, the frequency range is from 0 to 128 Hz. But now we apply bandpass filter and uh, apply this filter, and our low frequencies from zero point 0.5 and high frequencies 45. So our signal is in within the range. So here I take the file, read that file, and pick all the EEG data. We exclude any other signal, so we just type like raw EEG data equals to true and apply filter. After applying when bandpass filter, how so it will show you that now your frequency range is your bandwidth range is 0.5 to like here you will see what is your low pass band and your upper pass. Because here also you see like after applying your filter now, so your signal now in this range 0.5 hertz to 45 4 in this segment I am showing a plot comparison because it's important for us to see like what you done with your signal. So here what I did, I pick here first channel, like channel number 0, and the first window, first and second window, I take it. And also I take after filter signal and I plot a graph. For that I use matplot library. And here you will see this kind of filtering happen after applying band pass filter. So you will see here that before filter what type of signal are and after filter. Here I just choose your one channel because you have a 23 channels and I take it your channel number 1 and only 10 seconds state. And it's for just visualize purpose, like after applying your band pass filter, how it look like. Is there any have problem? Everyone understood? If anyone have a question, ask me, interrupt me. I don't have any problem. Okay. So now I move to another filter because I already explained you in our EEG signal, a lot of noise. So I apply band pass filter and second one is notch filter. Is basically uh, all we know like in most of the countries our power line supply is 50 hertz, but in some countries it's 60 hertz as well. So accordingly they choose their power line noise. So basically using notch filter I remove power line noise which interrupt your EEG signal. So here you will see uh, I hope like in when we are studying, we listen a term Nyquist theorem. I think all we are familiar about what is Nyquist theorem. So basically, notch filter work on Nyquist theorem. So here I range frequency. Here I use a NumPy library and NumPy library centers. So NP range. The sentence was is here like you select your start, stop, and your step size. So we want to remove 50 hertz frequency signal, so this we set as a 50. Then we type a stop frequency, which is basically a Nyquist frequency. So our sampling frequency is 256. So Nyquist frequency is that half of your sampling frequency. So we type int raw info as frequency by 2, and our step size is 50, because if your signal is 50, 100, 150, in this step size, it remove all this interface signal up to Nyquist frequency. And then we apply this filter to our raw data. Here as also I take it for showing that if I take it first channel and I take it 1 second data, 1 second sample, and give it the sampling frequency information. And if I take it from the samples from 10 second to 11 second, so I multiply this 10 second to sampling frequency and 11 second to sampling frequency. And we minus this window and we have a 1 second of sample. And if I plot the graph before as our signal look like and after that applying notch filter, so I take it X label and Y label as a time amplitude. So you will see here, after applying notch filter, it's look like your signals. Let's filter your power line noise. Now we move to our another noise, which is related to our eye blinking or our muscle activity. So for that we have a technique is independent component analysis, basically. So here what we did, we have a 23 channels, and in our channel, you see in upper side, like in here you will see, like here, we have a lot of data. Okay, and it depends on your purpose. Like if your if you see when you visualize your data and you see like in few channels your like more than large signal, it's a lot of large signal or a high spikes is not a worth it signal for you. Basically the very large signal is related to muscle activity or eye blinking. Most of the time where that kind of signal is related or indicated to eye blinking or muscle activity. So this independent component analysis is basically depend on some of your manual analysis, like how you analyze your signal. So that's why here you will see that I take it component IC and components equals to 20. So what is the mean of 20? Which is basically showing that uh, I assume that in my 3 channel, when I analyze all the signal, I see that 3 of the components of my whole data set, there are a lot of large signal. And in terms of it's not be more useful because there a lot of spikes. It is a very high spikes. So I choose or I separate like out of 23, I choose only 20 important signals. Okay, so I give it this theorem and component. I choose 20 important signals, basically a component. And this is a random state equals to 42, which is a random value, basically take it. And we apply a mix iter equals to auto means. It's automatically choose your 20 anode components and give it to you more like refined signal to you. Then we apply this filter to our raw data. Then I plot the graph. Uh, After applying this, also you define that it's showing which kind of signal in your these components. So I will show you here. When you apply this on your EEG like signal, so all the like channels converted into as a component. Yeah. So here I take it all 20 components. It starts from 0 to 90. So all are 20 components. And here you will see, here I choose only 1, 0 and 1. The mean of 0 and 1 is that after applying ICA, again you see that in signal, here's a lot of large component. It's just a manual value. When you see your signal more closely, so you see here ICA 012, yani 12th component was a largest signal. Yeah, it's a more higher signal. So rather than 0, 1, you choose 1 or 2. It's just example. And then I apply, like I remove all these signals and I apply this. So after that, it remove your eye blinking signal. Uh, After removing all the noise, as per your understanding, because in whenever we take our data set, they already mentioned that they already pre-process. But if you want to apply more accurate data, you apply pre-processing step as well, according to your which kind of data you take. Then when you remove all the noise, we apply normalization and threshold-based artifact detection. The mean of that we normalize our data. So how we normalize? If you have 23 channels of data and you want to set your mean, all the channels mean is 0 and your standard deviation is 1. So within 0 to 1, your all the channel of signal are there. So that's why we normalize our data. So we give it our data. And what is our normalization formula? Data minus mean upon standard deviation. So accordingly, I type here data minus numpy mean is take it the data from there and standard deviation. And it normalize your data. If you see an upside cell, here is it. Mhm. Okay. No problem. So after normalizing your data, it's showing how many channels in your EEG data is 23 channels and your samples is 2921600 samples in your signal. So if you can done up to normalization, but we have one artifact also, which is based on threshold based artifact. Suppose like in our EEG signal or what we say in our brain signal, a lot of type of noise there, a lot of type of signal there. Every signal is not for useful for us. You know, sometimes it's kind of a large kind of signal, which is maybe cross your standard deviation. Suppose you take after normalize your data is 0 to 1, but suppose your one of channel or a few of channels data is more than 1. So we take a threshold up to 5, like it's a plus minus 5. Like more than that, if kind of signal in your data, you take it as a artifact. So we take it threshold as a 5, and I take this as a bad pass. It basically numpy into hold the data, and normalized data is greater than threshold. That means if your normalized data is greater than threshold, we understood that signal as an artifact and we remove that signal. So we identify that whole your samples, 9,21,600 samples, out of that 26,454, it's bad sample. So basically they are the cross their threshold value. That's why we call it as a bad sample or we detect as a bad sample. So after finding these bad sample, you have two ways. Either you remove that sample directly or you convert the whole sample in a window time zone and then you remove. So I apply both the system, both the ways. So first way is that you remove all the sample. So here I remove, clean all the bad samples. And if I clean all the 26,454 signal samples, so after that I have a clean data which is 89, like 8,95,146. It's simple up to we remain. The second method is that bad window removal. So the mean of that is you convert your whole sample in a small chunk of windows. Suppose that I have a lot of samples and I convert whole sample, like I take it as a window, as a 5 second window, whole signal. So suppose my sample frequency is 256. So in 5 seconds, I have 1280 signals, samples, sorry. So my window size is 1280. But when you remove whole bad window, in case of that, you have a like uh, if in your window, suppose your 1208 sample in one window, and suppose your one sample is like bad or a large threshold value sample, we collect as an artifact in that signal. So it remove whole window. Or if it happen, your moreover signal is like drop. But here is that after removing all the bad window, you have only clean EEG data set, or you have only clean EEG signal. So this is also an advantage. Ki whatever signal you have, after removing that window, you have all pure EEG data. So what we learn here or in this set, first of all, we load data, import important libraries, we read our data, we load our data, then you visualize your raw data. Any file you can visualize through this. The mainly, at least you apply bandpass filter, whatever range you required. Like in our range signals, we have 5 type of waves now, like delta, theta, alpha, beta, gamma waves. But according to your application, what range you required, Here I take it 0.5 to 4.5. But if you want 1 to 40 years or 5 to 40 years, according to your application, you take it and you apply bandpass filter. Then notch filter is same. It's depend on your power supply, which country you are. Most of the countries 50 hertz power supply. So you apply 50 hertz Nyquist theorem, like notch filter. If it is 60 hertz, so you apply 60 hertz. Then for removing eyes, yeah, eye blinking, noise or muscle activity, you choose independent component. Uh, Here I take it 20 independent component. But if you want more precise, you can choose 15 components or you can choose 18 components so that it gives more accurate. But I take it as it's the average of like, okay. Then we normalize our data and we remove artifact which cross threshold value. And after identify all the bad samples, we remove that samples directly or we convert that samples as a window or whole sample as a window and remove bad windows where if one of your sample is bad, it remove whole window. So this is the basic pre-processing steps if you are working on EEG data. So, uh, before going on imbalancing and how we deal with imbalanced data, I want to ask everyone, anyone have any question?
Participants, if you have any question till now, then please better to ask now. No question till now. Okay, Anjali, go ahead.
Okay. Wait a second. One second. Second. Mhm. So I already told you that I take it EEG epilepsy seizure data. Yeah. So whenever we work in any data set, we are facing imbalancing like data set issue. So we have a lot of ways to work on imbalancing data set. So before moving to what code I write it here, I want to explain things like what type of uh, what type of technique we use for imbalancing data set. Suppose when you collect data, like a patient having a seizure, and the you all know like seizure timeline. Whenever a person having a seizure, maybe it's for 1 minute or 2, 3 minute or 5 minute. Suppose a 5 minute of seizure data. When we are collecting data, that person, we are collecting up to 1 hour data. And within that 1 hour, maybe that 2, 3 minutes of duration, we have a seizure data. And remaining of that is non-seizure type of data. In that situation, when you collect whole data, it's a kind of that imbalance because you have only 3 minutes of Caesar data and remaining 57 minutes of non-Caesar data. And in that situation, you have important to deal with this is imbalancing type of situation. So we have a lot of technique to deal with this kind of data. The data which I show here, they already mentioned like in which duration seizure occur. I show you one of the file which I downloaded there, like from this second to this second seizure there. So that will help me to as a labeled data. Okay. So we here I explain you four techniques. One is undersampling, oversampling, uh, smooth, and last one is data augmentation. Actually, I take a picture from Google Internet so that I visualize like how things like. Suppose this is your original data set, and this green one is suppose your Caesar data, and this orange one is your non-Caesar data, and this is whole your data. In that situation, you want that at least both the data types are at least balanced or that they are equal. So when we apply undersampling, what we did, we reduce this data. You will see here, like if you have a large number of data, you reduce this data and you take a few samples in between your segments and you equal your Caesar data and non-Caesar data. So you understood this word undersampling. So we already reduce a sample. But in oversampling technique, what we did, we increase our Caesar sample equal to our non-Caesar sample. So how we did this? Actually, we duplicate our Caesar samples. We a lot of times we duplicate that Caesar and you equally create uh, according your non-Caesar and Caesar. So these are two simple technique. Undersampling means reduce your sample. Oversampling is increase your sample or what we say duplicate your sample. So that help you to balance your both the Caesar or non-Caesar data or it's a two type of data if you have or if more than that. Then the third technique which I use here, which is mode, it's basically synthesizing your data. Uh, if anyone heard about KNN algorithm, in KNN algorithm, we take it as a nearest neighbor data. So what we say, like here you will see in this image, it's an imbalanced data. You know, a lot of non-Caesar and few of Caesar data. In KNN algorithm, if you know, it follow vector algorithm. So uh, here we generate synthetic data points using this algorithm. We create synthetic data points and we take it nearest points and we generate type of Caesar data so that we balance at both the data set. It's not like our oversampling. In oversampling, we duplicate our data, but here we generate new data set using KNN algorithm. And the last one, which I told you, data augmentation. In data augmentation, basically what we did, uh, basically we use random noise. And using random noise, we generate like a signal, or we said like we equal our Caesar signal to non-Caesar signal. So suppose that you have a kind of signal and you add the noise on that signal, and then both the noise and your Caesar signal generate another new signal. And this technique will not only help you in label data, but also where you have no label data, there also help. Now I'm here. We already know that how we mount. So these are the already few steps mounting data. Important libraries I installed here. We already know MNE, NumPy. sklearn, basically, I use this library for undersampling or oversampling technique. Then for synthesizing, which I told you, SM, SM2 technique, I use this library, inburn library, which actually helped me to synthetically generate your data. And this library basically work on KNN algorithm. So it help you to generate uh, data. Then I like download few other libraries, which is basically for random forest classifier, a training and testing data split set, and provide some accuracy and F1 score, which I explain you in end of this notebook. Why I'm taking it, because I'm showing like which method is good for this data set. So I download these libraries. I load this data. I apply bandpass filter and normalize the data set. Yeah. Up to here, whatever process we follow in pre-processing. So I just take it few process here, few steps here, and I normalize my data. Now I told you where I show you image, like in this file already given, in this data set already given that which file from which second to which second like your Caesar is occurred. So here is already given like 2900 to 9600. This second to this range having a Caesar data. And what I want, I just want all the data as as sample. So I multiply all the timeline to sampling rate, and it give it to me all the data in as a sample. Wait, take that. Yeah. So I convert my whole sample in all the samples, like if I know from start or end point, and I give it all these sample. The sample they are no Caesar, so I indicate as a 0, and the sample they are Caesar, I give it 0 1. So I label here like data from this is Caesar 1, and the data have no Caesar, which is basically a 0. So here just information like we convert our data to Caesar or non-Caesar. Now it's main important thing is come here. Like we learned like we convert our whole sample in window sample, and we learned like I take it as a 5-second window. So we have 256 samples in 1 second. So we have a 1280 samples in our window. So I set here 1280 samples in our in our one window. I take it two variables x and y. I take x, which is basically represent our EEG data samples, and y is basically represent our window length, like which window is representing Caesar data, which is one, or which data representing as a zero, which is non-Caesar data. So we take it x and y is a two variable. Now then I apply for loop here, and how I differentiate x and y. So all the samples, if I take it from I equals to 0, so uh, up to 5 second samples is put it in X array, or here you will see in Y append int label I colon I plus window size dot mean is greater than 0.5. That mean I take it here like in any window where Caesar are more than 50%, I take it as a 1. So here I put if your in your sample is Caesar more than 50%, let's take it as that. And I all put all the data here. For that I use NumPy library. And if I run this, you will see that we collect original class distribution, which is 7, 11, or 8. The 7, 11 is showing your non-Caesar window. And this 8 is your Caesar window. So you have a knowledge, like you have understood that in this within range we have a Caesar data, non-Caesar data. And now we apply undersampling, oversampling, a technique which I told you or I explained you in that image. So we know that in undersample we reduce our sample. So here what I do is here I reduce my sample. So I only take it each window. I take it only one sample, and rather all the remaining sample I put as a false and reduce that sample. And after reducing that, I concatenate all the samples in the x and y. And when I apply here, you will see that after applying undersampling, you will see here that your non-Caesar and Caesar window sample are 8. That means we reduce from 7, 1 to 1, 1 to 8. So now your non-Caesar also equal to your Caesar net. Here we balance our data, but you also see there we lost a lot of data. So in sometime in case of undersampling, we lost our data. Then second is oversampling. For that, we just want to copy our data, or we convert our Caesar data to multiply that. So that's why I copy that data and concatenate all the data to X and Y. And when I check this, here you will see that the oversampling class distribution is all are equal. Both the samples are equal. So now your class balance, but you already know that in oversampling, it's a kind of duplicate data, but it's balanced already. Then third technique, which is synthetic minority oversampling technique. basically where we synthetically generated data. So using this inward library, it's help you to generate your synthetic data. So here we type x flat equals to x reshape equals to x dot shape 0 and -1, and applying smooth technique here and apply this. So it converts in overt sampling, like it's basically using KNN algorithm, and it synthetic generate all these data sets. And all the samples are equal here. But it's more like to usable theorem, because here it work on nearest neighbors, or it generate your sample using the nearest neighbor data. Then all we know data augmentation, we add noise. So here I take a noise level is 0.01. So I minute noise I added in our sample. And after adding the noise in our samples, it convert that Caesar data in a more data, in more type of data, and noise added here. Then we concreted both X and Y as a sample and as a label data. And here is also similar. We balance our both data. So these are the 4 techniques. Up to here, you can use any one which best suit your application. Uh, the last step is just for showing, like if I use the all 4 techniques, which is better for me. For that, what I did, I convert all the data in 80-20 ratio, and I take it as a 80 as a training data and 20 as a test data. And I put it here. And when I check accuracy and affluence score of all the 4 algorithms, so I got this result. Like undersampling give it me accuracy is up to 50%. Oversampling is given to me 100%. Smooth is given to me accuracy is 100%. And data augmentation is given to me 98.25%. All F1 score are almost equals to 1. The data augmentation is 0.98. So moreover, this mode technique is more accurate as my observation, uh, because here we generate a synthetic data, and this best suit for your application. That's all from my side. So these are the 2 topics which I cover here: reprocessing and imbalancing data set. If anyone have any question, uh, please ask me. Uh, Surely
Hey, participants, if you have any question, then please.
I
Ma'am,
share
could you
I
please
share
share
you.
the.
Yeah. Sir, I share you link all the data set, and also I share these globe, like this notebook also.
Okay, I will share on means Canvas platform.
Yep.
Okay,
Yes. Yep.
so don't worry. Means if she can share with me, I can share with her on the Canvas platform. Yes. Yes. Any other question regarding the piece of code or something regarding the EEG? So we are heading towards now end of the our workshop. Okay, because we have only last 2 hours. That is the one session only. Okay. So if you have any question, then please we would be happy to answer. Maybe we can wait for 2 more minutes only. Okay,
Okay,
so
sir.
that if
Yep, sir.
if
Okay.
they have any question, then they can ask.
Yes, sir.
Okay, it seems that there is no further question. Okay, so thank you, Anjali, for joining me, sir. Okay,
Thank you, sir, to
so
giving me this chance.
with these participants, we will have a 5 minutes break. Okay, so we will be assembling over here at 3 again. So after 5 minutes, okay. And meanwhile, our next expert will join. Apart from that, participants, just to let you know that we have a validatory at 5 o'clock. Okay, to end of our MDP, and you have a quiz tomorrow. So please remember these two things and hope to see you at after 5 minutes. Thank you.